course, for calculation, the most important will be the fundamental theorem of calculus. But theoretically, if you want to prove something or explain something, maybe the mean value theorem is more convenient for us to use it. The mean value theorem. Oh, the condition is very mild. At any point, we cannot talk about differentiability because differentiable we mean a limit from both sides. Or in. Then under these very mild conditions, f of b minus f of a over b minus a. This is the average rate of change of this function of AB equals instantaneous rate of change at some number c prime of c Of course, this equality also can be expressed by f of b minus f of a equals f prime of c times of b minus a. Same. Geometrically, if a function f is continuous on AB, and the differentiable inside, interior to AB. So at endpoints, maybe you have a vertical tangent. The coordinate of this point is A, f of A. The coordinates of this point is B, f of B. And this quotient is the average rate of change. It is exactly the slope of this straight line. Okay, what is f prime c? It's the slope of the graph at c. Equals this one now. Yes, push parallel up or down, you will find a some place. Maybe more than one. Oh, sorry. Here. Maybe more than one position. Okay. Here, the slope of the function f at C1 is same as the slope of the straight line passing these 2 points. Okay? So this is the geometrical interpretation of the mean value theorem. A special case of mean value theorem is called Rawls theorem. Rawls theorem. The conditions of this theorem is, again, continuity on a bounded closed interval, and the differentiability is needed on or in. So, C, and the condition 3, f of A equals f of B. This number is equal to this number. So, the difference of these two numbers is 0. Geometrically, A, B, A, f of A, B, f of B. The graph of this function may be continuous on the closed interval AB, and the differentiable in the open interval AB. Then there must be somewhere whose tangent is horizontal. Whose tangent is horizontal. Maybe more than one position. Okay, so Rawls theorem is a special case of the mean value theorem. This theorem is easy to explain why. Let me explain this theorem. Okay, f is continuous on AB, and the differentiable on open interval AB, and f of A equals f of B. If this function is a constant function, for example, all values K so a constant function of course is continuous on AB. A constant function is differentiable on or in open interval AB, and whose derivative 0 everywhere, inside everywhere. So in this case, C can be any number interior to AB. Horizontal tangent, horizontal tangent, horizontal tangent, horizontal tangent, horizontal tangent. Okay. Now suppose there is some x, if not a constant, f at x is greater than this number, then there must be a maximum of f, because by extreme value theorem. There must be some, f has a maximum at some number, maximum. Okay, and this number is not an endpoint, because endpoint whose value is maybe here. But already the value of f at some x is greater than this number. So the maximum may be, must be greater than this one. And therefore, C1 must be interior to this closed interval by Fermat's theorem. F prime C. C is a critical number. Okay. This complete the proof. Oh, of course, another possibility is that if some number inside AB whose value is less than this value, then the minimum of this function occurs interior to this interval. And this one is again a critical number. So by Fermat's theorem, f prime c equals 0. Okay? So the special case of mean value theorem is easy to explain. From this condition, use extreme value theorem. F must has maximum and minimum. Okay. From this theorem, from this condition, if f has maximum or minimum interior to this interval, then f prime c equals 0 only. Okay. Of course, another possibility is the maximum and the minimum are the same. Maximum also the minimum means this function is constant. Or in this case, every interior point of the closed interval can be as the number c. Okay, no problem. This is exactly the first case. Same height. Okay, if some x whose value is greater than the value of fx at a, looks like this. At some x, the value of f at x is greater than the value of f at a, then the maximum must be interior to happen interior at the number interior to AB. So according to the Fermat theorem, the derivative is 0. It is the first case. Another case is like this. Some value of f is less than the common value at the boundary. Then if the minimum of the function f will occur at some interior point. Interior point is differentiable and by Fermat theorem, whose derivative is 0. Okay? So this section we use what we have learned from the last section. And this theorem can be proved by Rolle's theorem. How to use this one to prove that one? The key is to define some function, satisfy condition 1, condition 2, and this condition. This is not hard to define. This is the function f, and this is a linear function. Y equals, passing through this point. And the slope is if we consider the function f minus this one, f of x minus this one, then at x, f of x is here. Suppose this is g of x. G of x is here. So f of x minus g of x will be here. So the difference of these two functions, f and g, will be here is 0. 0. This is the difference of f and the g. For this new function at a, the difference is 0. At b, also the difference is 0. And this function satisfies the three conditions contained in Rolle's theorem. So there must be some place interior to A.